hyporheic zone remains. So 25 minutes to for question.
Sure. Thanks for reminding me, and thanks for chairing the session. Thanks for the invitation. It is Thanksgiving Day, so that's why I'm thanking everybody. Okay, I'm going to talk about a specific application of basic measurements, and it is an area that has been the focus of study for some time now. It relates to whatever happens between surface water and groundwater, which is an area still not fully understood, and you will see that there are quite some reasons for that, because from also the geomorphological point of view, the riverbed is a very dynamic environment, so that it tends to be heterogeneous, much more than one would think. Okay, first of all, let me drive your attention towards this issue. Geophysical measurements can give you very interesting information about the structure, but as we have seen, and as is the focus of this workshop, it can also give you information about the dynamics of the system. One key issue that I see in monitoring changes is that you must try and link those changes that you observe to some processes that you want to be able to model. Okay, and I think Frederick's presentation has been a very good example of this. Okay, of course, the riparian Hyporheic zone is interesting in many respects, but particularly, I would say, because it is a very reactive zone. So it is a zone where a lot of contaminants, solutes, react, particularly in the Hyporheic zone, and this exchange of waters between the Hyporheic zone and the rivers is actually changing the water quality both ways. So first, I will show you an example where there is no dynamics. But the purpose is also to show you the complexity of this kind of systems. Here we are in northeastern Italy, and we are at the confluence between two rivers, okay, which are very dynamic rivers. And you will see that investigation of this area, the area is on the side, so in the riparian zone, properly said, okay, is not as easy as you might think. Okay? So a lot of techniques have been used, including borehole, cross-borehole ERT, refraction seismics, surface wave analysis, seismic surface waves, and so on. Let me show you first electrical resistivity results, because they are quite peculiar. Okay? If you look at the resistivity range, you see that the water table is roughly here, which is the level of the river, not so surprising. This is actually gravel, but by and large this is kind of a mix of gravel and finer sediments, right? And you have a very large resistivity above the water table, but also below the water table. So basically you don't see the water table, which is kind of surprising as a starting point. And then you run some classical seismic measurements, like this refraction tomography results. And you see some correlation between this high here and this high there, but really not enough to explain. Also above the water table here, you don't see a lot of correlation. So it's actually a big question mark. Why do we have these strange DRT results? By the way, they're not on one section only, huh? They are everywhere. Okay? And the approach we took to try and solve the problem is we use surface wave analysis, and particularly MOPA, which means multi-offset analysis of phase analysis. It's interesting because you can get really two-dimensional images in terms of S-wave velocity. And here you see the result along one of the lines. The interesting thing is that you see here a very strong velocity inversion in terms of shear wave velocity, which you wouldn't be able to see, you are not able to see using classical P-wave refraction. If you compare with a P-wave refraction, you see that actually this velocity inversion is totally lost below. So you see this body now well delineated, right, where it should be. And if you if you compare the basically the shape there, okay, with the ERT image, you end up with a mixed explanation for this strange high resistivity body here, which is actually not a single body. It's actually a mixture of two things. One is a more compact, cemented gravel below the water table. The other one is that here you have gravel, unsaturated gravel, and here you do not have gravel. You have like a mixture of gravel and silty clay, okay? So it's really very heterogeneous. You must be careful when you interpret this kind, particularly ERT results, because electrical resistivity may depend on different causes. Okay, so you basically have two different causes for something that looks like a single resistive body. This is just to give you an idea of the complexity. So let's move to the hyporheic zone, because if understanding the riparian zone is complex, well, you can actually walk, okay? It's much more complicated to understand the hyporheic zone, because hyporheic means you are below the river, right? And that this is actually the most interesting zone, because here is where all the reactions take place. So I'll show you one example. It is we've been monitoring the site for quite a long time now. It is a relatively small catchment. It is a head catchment in the Alps, and you see here the river, which has been clearly engineered. It is straight. You know, nature doesn't like these kind of straight rivers. So you can expect that there is something complex in the surface there. So first of all, we started with classical measurements, right, from the surface. So this is the ERT measurements across the valley. The river is flowing down from here to there. And this is a smaller scale GPR measurement. And you see quite a few things, but at this scale, look at that, we are talking about 350 meters here and 70 meters there. You don't really see much details about what's going on. You cannot see that. The resolution is far too coarse. In the GPR measurement, you see something that looks, and I actually believe it is, the bedrock, because you have a lot of coarse sediments filling the valley. So you actually have an aquifer that is running downstream in this valley, and is actually interacting with the surface waters. Here you see Matteo Rossi, who's sitting somewhere here in his young age when he was doing measurements for us. Afterwards, after these measurements, we decided to go in much more detail. We wanted to understand what the processes were within the hyporheic zone. Actually, I have to acknowledge immediately two European projects who actually were focused largely each on this site. So we decided to install, using directional drilling, an ERT electrode cable below the river, and also a DTS fiber optic below the river. They're not in the same pole because we installed them at different times, but they are basically parallel to each other. So we end up having this kind of configuration. This is for ERT. Well, of course, it's kind of the grid we use for inversion, but just to give you a feeling, so the creek, or the river, is actually flowing nearly all year round. It's here, and we're talking about cables that run about 80 meters from site to site. Okay, this is the ERT configuration. We also completed the configuration using 24 surface electrodes, so we have 72 electrodes overall, which are surrounding this hyporheic zone to a depth of about 5 meters. There is no scale here. And basically with the same configuration, we also put the DTS fiber, and luckily Freda already explained what DTS is, so I don't have to do it. Okay? This is actually using a Raman effect. So it's actually two fibers. They go from one side to the other. They are coiled here, and then they go back. So we will see the effect in the data. Okay, this is the image, the absolute resistivity image, the typical resistivity image we get from this kind of measurements. Of course, we want to focus between the electrodes. And there are several features here. Okay, first of all, the water table is near, well, it's not exactly at the level of the river. It is a few tens of centimeters below the river in the surrounding aquifer. So the river is actually losing, it depends on the season, like generally losing water towards the aquifer. Second, the heterogeneity is fairly large. We go from 2000, which means a relatively clay gravel, to something that is well below 200 ohm meters. And given the electrical conductivity of the waters in this kind of head catchments, this means that this stuff here must be fine sediments, and they're just below the river, okay? Which is one of the key question marks we're still struggling with today, okay? Because this body is there. It's not only in the section that we see here, but it's also, this is not a very good presentation, but we ran an ERT image from the surface along the river bottom, and you can see that this area above, these are the gravels, but above that you still have the same high resistivity body. So it's actually running below the river. So one hypothesis is that this has been set in place once the river has been engineered. So all of a sudden the river started to flow into clean gravels, losing fine sediments, and it created its own bed in a way, okay? Which is distinctly different, electrically speaking, from the surrounding. The other thing is that even though here, of course, I kind of pushed a little bit the resolution or the penetration to a larger depth than I should have, I also see the bedrock, okay, at the same depth where I see it in the nearby GPR measurements. So we started to do seasonal monitoring, and this is another key issue, and I also was talking to somebody in the coffee breaks about this. Sometimes you have the ambition of looking at changes over time, but remember you have a sampling problem. You need to sample frequently enough to reproduce the processes. Otherwise, you're going to alias your processes. You will not be able to understand the processes. We all geophysicists here. We know what alias is, right? So even though, of course, there is some information in the individual pictures, if you interpolate between the pictures, you might get the totally wrong image about the processes. So let me discuss a little bit in detail here. These are differences to actual ratios with respect to a background that was beginning, say, late April. This area is covered with snow over winter, so you cannot really run measurements in the winter time. So this is just the beginning of the thawing season. So this is May with respect to late April, June and July, late July. And you clearly see some differences. In particular, there is an increasing resistivity below the river, particularly here in June versus April, which might be, but with this kind of sampling it's difficult to say, might be linked to the infiltration of fresh water coming from glacier thawing during this season, during the summer. This water is cooler, so it is more resistive, like Frederick said, and it is also, it has much less ions than the water that is generally running in the river for a long time, because the water is coming from groundwater, so it has a longer pathway, so it has higher ionic concentration. So it's not really a surprise to see that in the middle of summer you have an increase in resistivity, because you have more resistive water that is infiltrating the system. If we look at the DTS measurements, let me explain first what we're looking at. This is the mean of the two halves of the fiber going back and forth, okay, at different times. So you see here, this is April, May, June, and late June. And of course, not so surprisingly, temperature goes up during summer. In particular, you see here the tail is actually very close to the surface. So you have the temperature, it's more extreme in a certain sense, but it has a temperature that is close to air temperature. Look at temperatures are pretty low here, 4 to 12 degrees. The left bank tends to have higher temperature than the right bank. And the river also has a different behavior. In particular, you see here in the middle that you have this increase in temperature, this more kind of variable behavior in temperature across. But it's difficult to say anything because this is really undersampling over time. Okay? However, first let me explain the difference between the left and the right bank. Okay? The left bank has also some artificial lakes on the side that are there for recreational reasons, that are basically draining water into the stream very close to where we're measuring. So not so surprisingly, these lakes are heating water, and the water is likely that is coming down this way at the surface is warmer than the water coming down the stream. So it's not surprising that the left bank is warmer than the right bank. But let me show you one telling example about the time undersampling. Here you have the same data set, right? Exactly the same, with the same colors, with one more line, okay? The extra line is this one. This is okay, we still have this one, 30th of June. This is the next day, okay? So the blue and red are 1 day, less than 1 day apart. So you can immediately tell that there are some processes that are happening at a much, much finer time scale. Because the difference between these two is not much more than the difference between these two. So how am I sure that this difference between these 2 dates is not given by the different time during the day? And in fact it is due to that, okay? So these two are very, very different, even though they are one day apart. If you look at the situation in the river, of course we have some probes in the river. Okay, let me guide you through this. This is water level, the red is water level in the river. And of course it has a daily cycle, because thawing is happening during the day, not during the night. It's shifted a little bit because it's thawing during the day and then the water is flowing. At the same time, resistivity is following that. Okay, so which means that the water that is filling more the river is more resistive water. And not so surprisingly, the temperature is doing exactly the opposite, with a slight delay with respect to head, but say very much in line with the resistivity. Now you may argue that temperature is explaining resistivity changes alone, but if this is like a 6 degrees change, so it will be 12% change in resistivity, but resistivity changes by something like 30% during the day. So there must also be an ionic effect there, unless the situation is becoming highly nonlinear at low temperature, which I'm asking Fred for that. Highly nonlinear. So highly nonlinear. Well, let's see. Okay. So clearly there is a pump at the top that is driving the situation during summer. And you can see that even in the ERT time-lapse imaging at a very short time scale. So here you see that this is a ratio between this moment and this moment. So it's a full day, basically, cycle. I'll go quickly through that, because really it's not adding much. You see some changes, okay? Some changes below the river, blah, blah, blah. The main change, though, with respect to the beginning, happens about 1 day afterwards, okay? So you see this change. This is a major change. Well, major. It's 5% less resistive in this zone. It's actually more. So it seems that you have a signal that is somehow has some delay, right? But this is not really a surprise, because of course we are looking at what happens below the river. So there is a time constant that depends on the hydraulic conductivity, especially. Okay? Okay, this is last image. And the DTS measurements, temperature measurements, also tell pretty much the same story. Now, of course, it's a long sequence here, but you see the changes from a certain time. You have a substantially increase in the temperature below the river, and then it's gone back and forth and so on. Okay, so you have this band. Okay, below the river, clearly you have much more dynamics than you have on the right bank. And of course, in the tail, that is measuring the soil temperature, you have basically no change. The left bank is also affected by the drainage of the lakes. Okay, so this is confirming that this is a signal due to infiltration from the river, and of course also from the drain. But I want to stress that in order to understand these processes, you really have to run some models. Okay, so this is a full three-dimensional model of flow. It's actually also unsaturated flow, but unsaturated flow doesn't really matter here, and transport. And I'll show you just some example, one example of modeling using two materials. So this is what we expect to be fine electrical conductive material below the riverbed, and the rest is a glacial till. It's more electric, it's more hydraulically conductive. So it's two orders of magnitude difference. Boundary conditions here, we're talking about 75 meters stretch, and this is 14 meters. You have to know that there is a jump here in the river. There is an artificial jump. It's actually expected to control the infiltration below the river because it's driving water. The head is actually, there is a sudden jump in the head if the river is flowing at the same stage. And so this should be driving more water below the river, okay? 3 minutes? 3 hours?
3 minutes.
I have to buy you a new watch because I think you have a wrong watch. Okay, okay, boundary conditions are, well, I'll show you here. So the boundary conditions are Dirichlet boundary condition here on this side, on the upper side, normal no-flow boundary condition along the sides, and of course we have the forcing conditions of the river, which are changing over time in terms of head and concentration. So we really didn't have to do much to match reasonably the head in the piezometer. So this is the real is blue and the model is red. So it's a fairly good response, but it's no surprise because the head is easy to match. Okay, we are really close to the river. We are just a few centimeters below, a few tens of centimeters below. Basically, the system is following the river, right? Well, I cannot prove it, but if I change the hydraulic conductivity by 1 order of magnitude, I will still match it, most probably. And then, of course, we ran some transport models. Let me see if I can work. Yeah, okay. Let me explain what happens. Basically, the groundwater. This is a full 6 months simulation. It's just lump, right? The groundwater is much more conductive than surface water. So, particularly from April, beginning of April, like this simulation is shown, to the end of June, we have this fresh water that is much more resistive, that is actually penetrating in the groundwater. We're talking about 1 order of magnitude difference in electrical conductivity. It's not small. Okay? And you see here the jump. We basically, you see also here this section that is where we actually can observe. We observe there in practice what is happening in the Hyporheic zone. So we want to compare what we model and what we observe. So, of course, this is fine material. So we use like a Waxman and Smith kind of formulation. The rest is probably be okay with an Archie's law. You see the effect. Of course, we can easily match the resistivities because we have all the tuning knobs, right, that we can use. The interesting thing is you see this kind of behavior here of concentrations, which is due to concentration, which is caused by the low hydraulic conductivity of this layer. But this is probably a wrong assumption because if I compare the time-lapse measurements, okay, this is exactly the same times. The scale is different because here we are focusing around the river. And the difference is, the last difference is between these 2 points. So this is, you can clearly see that major changes happen exactly in that level, in that layer. So even though it is highly conductive electrically, it's not necessarily low hydraulic conductivity material, right? Which is not obvious. You have to look at these differences and convince yourself that that's the case. Okay, conclusions. Well, first of all, we know how geophysics can help both with structure and dynamic processes. And I would say that we have shown that directional drilling for EIT monitoring is very interesting for the Hyporheic zone, for seasonal dynamics, and also for short-term monitoring. In this case, resistivity ratio changes are linked to the river flow rate changes. I think this is quite common in the Alpine region. It's also some work done in Zurich some time ago on the Thun River. Thun River showed the same. I would say DTS monitoring is also an interesting add-on because, well, I didn't push it in this presentation, but of course you need to distinguish the effect of temperature and the one of concentrations if you want to understand what's really happening. We observe the temperature delay, and that is consistent in ERT and time and temperature data. But again, let me stress that you really need to do some modeling, because the model is incorporating your prior information, your conceptualization of the system. You have to test that in the Galilean sense against your data. Okay? Otherwise, it's no science. Okay, thank you for attention. Thank you for all collaborators and the EFP project for actually funding this research.
Thank you, Giorgio. So we have time for questions. Frederick.
Yeah, thanks. For the transport modeling, is it transport, is it temperature?
No, at the time, for this time, we actually convert, well, resistivity is not being, even the probes can give you electrical conductivity which are compensated for temperature, right? We didn't use that compensation. So we basically took resistivity as a tracer, if I can explain that, if I can say that. So we converted that into concentration, and we just had the transport as if there was no temperature effect. Okay? So the temperature effect
no
is
density effect.
No, density is no.
Okay.
Density is really small.
Okay. Because in the range, I mean, it's a bit larger temperature, but we do see some effect in the well, although.
Well,
but I think
here you have lighter water on top of
yeah.
well, yeah.
Okay.
So
it's a solute. So how did you calibrate the solute transport? So I get the flow is with the head, and then the solute is against what?
Well, it's not calibrated.
Okay, it's just a simulation.
As you see, we have a strong discrepancy back into hydraulic conductivity, which is a proof that actually matching the head data will tell you nothing about hydraulic conductivity.
And then the last question, if I may, because you kicked me out at my keynote, so I have to speak more.
One more. Then I have a question for you.
Yeah, sure. Do you model the river depth in the inversion? Because we couldn't quite grasp it.
Basically, the flow in the river is much faster than in groundwater.
Yeah, but I mean the layer of the water is in there?
Yeah.
In the model?
Well, it is not flowing. It is not modeled as flow. It is a head boundary condition. It is a dish layer.
Yeah, for the flow, but for the imaging part, is it in there?
No, it's not.
It's no flow. I mean, it's fixed.
It's fixed, but remember that the conductivity of water is much less than the conductivity of groundwater. So it is not really affecting things much. And we're talking about in the low flow situation you have like this, in the high flow you have like this. So,
yeah.
by and large,
Okay, thanks.